Let's start. Okay. Welcome everybody to our topical seminar series on hadronic, atomic, and nuclear physics at the University of Barcelona. Today we are very happy to welcome Axel Pérez-Obiol. Axel is an alum of our group. He graduated with a PhD under the supervision of Asum and Bruno in 2014. That's after his undergraduate and his master's degree in Barcelona. He then moved on to the Czech Republic, to the Nuclear Physics Institute for postdoctoral position from 2014 to 2017. And then, as we were just talking about, he moved to Japan, to Kochi University. And he's just made his first step coming back into Barcelona. And in the 1st of April, he just joined the quantum group at the Barcelona Supercomputing Center, where he's working on, I guess, quantum computing and quantum algorithms. But today he will be talking about something that I guess we are more familiar about, looking into ab initio description of the hypertriton decay rate. Okay, Axel, thank you very much for coming, and take it away. Axel is happy to take questions as he goes along, by the way, so feel free to ask. All right.
Yeah, so, okay. Hello, everyone, in case I didn't say hello before. And thank you very much, Arnav, for the introduction and also letting me speak about our work on the hypertriton decay rate. As he said, I'm now at BCC, but I did most of this work in my previous postdoc. It's been quite a long-term project, and also in a very collaborative one. So I did this together with Daniel Gazda, from Czech Republic, I believe he's here, and Eli Friedman and Abraham Gal from Israel. So yeah, it's most of what I will say. It's been recently published in this reference here in Physics Letters B by the end of the last year. Some of it's not there. Hopefully it will be in a paper that should be published by sometime during the second half of this year, hopefully. Or at least you will see an archive, so wait for that too. Yeah, so I will talk about this computation on the decay rate of this very specific hypernucleus. And how do I go on and pass the slide? Okay. So yeah, let's go with the outline. The main message of this talk is this calculation of the decay rate of a specific hypernucleus, the lightest known hypernucleus. And what are the most relevant effects and how we compute it, right? So I will first start introducing this hypernucleus, namely the hypertriton, and motivating it a bit, offering a bit of background, both theoretical and experimental, and we're asking in the first place why the hypertriton and why this decay rate. And then I will go on and talk about first how we go from a partial decay rate to the total lifetime, which is at the end more interesting. We will focus only on a partial decay rate, and then how we get the wave functions that we need as input to this formula, to this decay rate, and then also final state interactions and what are the main contributions to the weak operator, the weak transition. And then, by the way, do you see my mouse?
Yes, we can, yes.
Okay, great. Yeah, I will end up showing the results, summarizing the results, also tackling a bit the problem of uncertainties in this calculation. So yeah, the hypernucleus we are studying here, it's the hypertriton, is the lightest known hypernucleus, so a nucleus with strangeness. And it consists in a bound state of a lambda proton and a neutron in isospin 0, then spin 1/2 and positive parity. This lambda is very loose. Its structure can be roughly understood as this proton-neutron cluster in an S-wave, so a deuteron-like state, and then this lambda very far social distancing at around 10 Fermis. 10 Fermis is a lot in comparison to this typical 1-2 Fermis between the proton and the neutron. So this lambda is very far, is very loose, and this leads to question how much different is the decay of this lambda, which is almost free, with respect to the lambda when it is actually free. So what's the naive expectation is that because the lambda is almost free, the lifetime of this system should be very similar to that of the lambda in free space. So does this hold? Is the influence of such a small nuclear medium really small or not? In both cases, the lambda in free space and the hypertriton, the decay is mostly non-leptonic. That is, the weak transition is from a lambda to a nucleon and a pion. About 2/3 of that is the charged product, so proton pi minus, and 1/3 the neutral one, so neutron and pi zero. So yeah, that's the main question that motivates this calculation, and that nuclear physicists have tried to answer for very long. Well, or at least I guess as many nuclear physics questions, right? The lifetime of the lambda is well known, or with some precision, 263 picoseconds plus minus 2. What is not so known is the lifetime of the hypertriton and also its separation energy. You can see that we know it's low, but it's just 0.13 MeV, but with some uncertainty. So yeah, starting with experimentalists, they started to answer, or to try to answer this question already in the 60s and 70s with emulsion, nuclear emulsion, and bubble chamber experiments. You can see the data in these blue points. So it's only 6 data points, 6 points with their uncertainties, and you can say that they did not really reach any conclusive answer back then. Even some points seem quite contradicting, right? So that's for these old emulsion and bubble chamber experiments. You have the reference here, and then the 80s came, 90s, 2000s, very interesting decades, but not really much for hypertriton data. And then during the last decade, heavy ion collision collaborations, namely STAR, HypeHigh, and ALICE, have picked up this problem and provided us with new data. But as you can see, also not really converging to any definite answer. So the data, both in the old experiments and the new ones, are very disparate, very spread, and with some uncertainties, even some contradictions. And this is known as the hypertriton lifetime puzzle. This is spread of and somewhat contradicting data. So here I put the statistical and systematic errors, and the first here in the blue points are 6. Here the first 5 are published. The last 2 I included 2 quite preliminary results that I took from talks in web seminars like this one, the one from ALICE and STAR. So there is some distinction here between published and preliminary results. But anyways, it's still a bit puzzling, and they seem to indicate that the lifetime seems a bit shorter. So this nuclear medium influences in the sense that makes this system decay a bit faster than the lambda in free space. And then here I selected some of the theoretical work, which started also very early, at least since the first experiments in the 60s. And we can classify them in different manners, but I think one first important distinction is whether they approximate the wave function into 2 or 3 body. So because this system can be understood as this deuteron plus lambda, some people assume a 2-body wave function where one of the bodies is this proton-neutron cluster. And then the other distinction is whether they do the full calculation or not, explicitly integrating over final states and so on. So Reid and Dalitz in the 60s, they introduced this closure approximation, and other people too. They use a simple variational wave function, I believe a product of one body wave functions properly antisymmetrized. Then Congleton picked up this in the 90s, assumed this, as far as I know, the first this deuteron plus lambda wave function with the simplification. And then in 98, that's more than 20 years ago, it was the first and also last, except ours, genuine free-body calculation. So that's the only one where they explicitly considered all the partial decay rates and the corresponding microscopic wave functions with solving the Schrödinger equation, namely the corresponding Faddeev equations. And the input to those equations were these Nijmegen soft-core and N plus Yn potentials. So those are realistic interactions, but they don't do so well for hypernuclei, starting with hypernuclei with 4 baryons. So that already motivates for an update in this calculation. So to do again a full 3-body microscopic calculation with new or let's say state-of-the-art EFT potentials. And then I cite here 2 recent works, that from Gal Garcilaso in 2019. The main message there was that the final state interactions, so pion nucleus strong final state interactions, it's relevant. It enhances the decay rate in this case, so that should be considered. And then there is also this work by Hildenbrand and Hammer last year, where they go back to this simple wave function, 2-body wave function, but they do this nice EFT approach where they consider the separation energy of the lambda, which is not well known with precision, as the small scale of this EFT, and they found that it seems not much dependent on that. And in general, they find a lifetime somewhat larger, so a bit in opposite direction than experiments, I would say. And what we do is try to fill some of these gaps left by previous theorists. So our approach is somewhat different. We focus on a partial decay rate, and from that deduce the lifetime. I will show you how we do this. But focusing on this partial decay rate allows us to study it much better, to include all the different effects that might be relevant, namely this final state interaction of the pion. We do a full microscopic calculation with EFT potentials as input. We include the sigma. I didn't mention this here because it was really not included, but as we will see, this is relevant. And then we also study the relation to the separation energy. And this is motivated by the fact that in this picture, you can, I hope this is intuitive, as the lambda is more and more free, so the separation energy is less and less. This should resemble more and more to the hypertriton lifetime. But this is not well known. So this is what motivates to study this, to make this analysis in terms of separation energy. And we will find, well, the main message is that these 3 effects are very relevant, but there is a strong relation with separation energy. And in this deduction of the total lifetime, we find a lifetime that is somewhat shorter, or considerably shorter than that of the lambda in free space. So to summarize a bit this background or this introduction, we have this hypertriton lifetime puzzle that's mainly an experimental puzzle, and it should be eventually resolved there with more data and more precision and converging to some answer. But meanwhile, theorists can do their predictions, their models, and study the uncertainties and so on. We saw that there is a lot work done in the theory side, but also a lot to be done, in particular to update this microscopic calculation with EFT potentials and include all the possible effects. And then in more general terms, also this is the lightest known hypernucleus. So in a sense, serves as a bridge between the more fundamental nuclear and hypernuclear forces, and understanding better heavier hypernuclei, strange matter, and neutron stars. So in the last talk we saw this, I believe last two talks were about ab initio methods in this seminar cycle, and it was discussed how, or shown how this nuclear landscape, right, how ab initio methods did pretty well for a big part of this chart, and how in a sense they conquered this chart for heavier and heavier nuclei. But you can also explore in those ab initio methods in the strangeness direction, right? Of course, the terrain there is much more uncertain because of the lower amount of data and quality of the data, but it's good to test ab initio methods in that sector too, in the strangeness part. So we also do that with this computation, and in broad terms, understanding the hypertriton is a first tiny step in understanding all these things better, right? So we have these three main motivations, and I hope that with that I got you somewhat interested in this hypernucleus for those who you weren't, and known a bit why is it interesting. And yeah, with that, let's go to the main part of the talk. So as I said, we focus on a partial decay rate, but there are 8 contributions to the total decay rate. So how is it possible that we infer something reasonable from the total decay rate or the lifetime if we only compute one? But it is possible, and in short, this right column, third column, is very small. The second one can be very well related with the first one, with the isospin 1/2 rule, and then within the first column, the 2-body decay rate can be related to the 3-body and 4-body with the experimental ratio coming from bubble chamber experiments. So these first and second are called non-leptonic modes. They are the biggest contribution, and these are called non-mesonic. They are, maybe here they are somewhat confusingly named after what there is not in the final product instead of what there is. So here there are no leptons, in other decays there are, but here there aren't. So these are called non-leptonic, but there are mesons, and in the right there are no mesons, so they are called non-mesonic. Just some clarification. Anyways, this experimental ratio between the 2-body decay rate and including the pion minus and including all pi minus, it's 0.35. This is taken from the old bubble chamber experiments. It has some uncertainty, but it allows us to relate this 2-body decay rate with the total one, including pi minus. So that's the first step. We just divide by 0.35 our partial decay rate. The second one, the second step, is to use this isospin 1/2 rule. I'd say this is very well sustained by experiments. It's a phenomenological rule, but yeah, as I say, it's sustained by phenomenologically. And you just multiply, so this is an isospin relation, and you just multiply by 1.5 the left column to obtain all the non-leptonic modes. And then finally, this is very small. So this was estimated to be about 1.5% from the non-mesonic decay, and then you have the pion through absorption. So this is I have the videos on top of some of the formulas. I hope you don't. Anyways, I want to mention that this interaction here is pretty relevant if you are really interested in the lifetime of the hypertriton. There are effects that are much larger than this, but this interaction I want to mention, it's very important because some people here have worked a lot on this one. It's very relevant for heavier hypernuclei, where this final nucleon is Pauli blocked because it does not have enough energy. So how you give more energy by not emitting the pion, and that's this interaction. So yeah, that's our protocol. I will focus in the rest of the talk in this partial decay rate from now on, but yeah. So that's the main protocol. Basically, three multiplications, 1 over this ratio, 1.5, and this 2.3% added to the total non-leptonic mode. So that's the, let's go on now and focus on this partial decay rate. Here is the formula for the computation of this partial decay rate. It has mainly 3 inputs: the nuclear wave function, so hypertriton and helium-3, the pion wave function, which if you not consider, so if you consider only a plain wave, it's trivial, but if you consider the final state interactions, there is some work there. And then also the weak operator. So what are the different contributions to this weak transition? And I will now focus on these 3 different inputs. Of course, there is also some work in developing this matrix element. It's not trivial. This depends on the different amplitudes in the wave functions. I don't really want to bore you with developing this and Klebs-Gordon and so on. But because other people have considered these simpler wave functions where it's just a 2-body wave function, I will write down here just, not for the details, but to show you that we can always, this is a more general formula, we can always just pick up the corresponding amplitude corresponding to this S-wave deuteron plus S-wave lambda and the corresponding for the helium-3. And if you do this, you can develop this whole matrix element, and you find this quite simple formula where you already have, so these 2 terms factor out with a nice factor, 1 over 36, and then you have some kind of form factor which comes from the overlap between those wave functions. And so the motivation behind this formula is that this amplitude for the hypertriton, it's about 96% of the probability. So this is why some people assume this simpler formula, right? But as we will see, we can compute only this, and it's not a bad approximation, but it's also not enough in terms of the decay rate, considering all the possible quantum numbers in amplitudes in the hypertriton wave function increases relevantly the decay rate. But it's always good to test. So back to these 3 main inputs, I will start with the nuclear wave functions, how we compute them, and then go on and talk about the pion and then the weak operator. So for the hypertriton and helium-3 wave functions, we use the Manybody ab initio Gaussian model. So this is an ab initio model, so all particles are active. There is no spurious center of mass or rigid core. The Pauli principle is exact, and importantly, it allows us to input realistic baryon-baryon interactions, and also we can control the approximations. So here on the left, we have our typical Schrödinger equation. In the left side, we have the kinetic terms. So these are the input potentials, the 2-body nucleon part, the 3-body nuclear part, and then also the hyperion nucleon. And this is at the end an eigenvalue problem, which we have to solve to get the wave function. And so for this, we need a basis for the wave function. That basis will need a coordinate system, and then also a specific potential that we'll input here. So starting with the basis in this no-Gaussian model, it's used the a-particle harmonic oscillator basis. It has a certain frequency, the frequency of the harmonic oscillator, and then also this N-max, which truncates the basis. So you need to truncate your harmonic oscillator basis if you want to compute this in a finite amount of time, right? So it has these 2 values that define this model, the omega and N-max. We will talk more about those later. For the coordinates, we use the relative Jacobi coordinates. So we have the center of mass, and then this relative coordinate between these two particles, and then the relative coordinate of the third particle, which in the case of the hypernucleus, it will always be the hyperon, the lambda or the sigma. And this implies a set of basis states of quantized angular momentum and spin. So we divide this into a cluster of two particles, which has certain angular momentum, spin coupled to J. N1, 2, and N3 are indices which index these bases. Good. And then we also need the input potentials. For that, we use the state-of-the-art EFT potentials. So effective field theory, I'm pretty sure all here know, but it's based on a separation of scales. You have a long-range part and a short-range part. So you need a cutoff scale that divides those two ranges. In the long range, you model with the interaction with explicit degrees of freedom at that scale, namely the pion, kaons, and eta exchanges due to chiral perturbation theory, Lagrangians. And then the short part you parameterize with some low energy constants. And these lower energy constants need to be fixed by experimental data at that scale, right? So we use for the nuclear part the next to leading order SIM family. As we will see, this is a family of 42 Hamiltonians. SIM is because it simultaneously fits scattering and energy data. And yeah, for more, you have the reference here, although I believe you know well this potential. And then for the hypernucleon sector, we have, of course, less data there, and the potential that we use is the leading order one by Polinder and Yuli group from 2006. So yeah, any questions here? Or? So fine. So
yeah. Axel, I wanted to ask: is there no three-body hyperon nucleon contribution?
No three-body hyperon nucleon. Sorry. I believe there is not enough data for the EFT guys to fix it.
All right.
Axel, yeah. Sorry, it's Albert.
Yeah.
Have you checked which is the contribution of taking into account the lambda and sigma and mixing, or you cannot decouple it? Or
sorry, I was looking for your video. The what? The lambda sigma n mixing.
Yeah, from the slide I see that you include the the mixing, right? And which is the role of including the sigma n? Because
yeah, good question. Also reminds me that I forgot to talk about this, to tell you the truth. At least I wanted to mention that this importantly, this hypernucleon potential includes this mixing. So the strong force in chiral perturbation theory, it allows to mix. So the lambda can turn itself into a sigma by interacting with the nucleon, right? And back to a lambda. So this is included at this leading order. And what is the role? This is, as far as I know, it's necessary. It's actually essential to fit the data. If I recall well, probably Daniel can chime in.
Yeah. At some point he explained me that, but
I believe
for this particular case, I don't know.
The state of the hypertriton and also for consistency, right? Yeah. And then beyond that, in terms of this calculation, if you have a sigma component in your wave function, the decay cannot only happen through the decay of the lambda, but also that of the sigma. So the sigma in free space also decays in a particular way, and you have some weak vertex that it will be sigma nucleon pion, and we will include that, and that will be relevant. I'm not sure if that answers your question.
Yeah, it did. Thank you.
Yeah. Yeah, so thank you for reminding me. This is an important part, actually. Yeah, so this is the many-body model. As we will see when talking about uncertainties and parameters or couplings, there will be 2 levels in this calculation, or actually 3 during this talk. So first there is going from the partial decay rate to the lifetime. We already talked about that. Then there is the many-body model, which is defined by these 2 parameters, the frequency and max. And then there is the input EFT potentials, which are not fixed. There is, as I say, this is a family of potentials. It will depend on cutoff and the amount of data that you include in the feed. But yeah, so back to our talk. Yeah, so we want to check that this many-body model is actually doing well, at least for the wave functions that we are using in terms of the energy, finding a bound state with the correct energy. So in the nuclear sector, we have 3 bodies, so we should at least reproduce the helium-3 and hydrogen-2 or deuteron wave function. And we can see that in that case with Nmax, remember Nmax is it defines the maximum quanta you include in your harmonic oscillator basis. So at Nmax equal 30, we see that it's very well converged with a very good accuracy of 10 to the minus 3 MeV and for a wide range of frequencies. So it does not depend on that. And here I put the 2 energies, the one with input next to leading order sim potentials, and the experimental one, to show you that it does indeed do well. Then for the hypertriton, the story is a bit different. As we were saying, the hypertriton has this very loose lambda in terms of wave function. This means that it has this tail. It spreads to very long distances or very low energy momentum. The relevant contribution. So at low momentum, the wave function is still very relevant. And that makes it harder to fit even for the maximum Nmax we consider, which is 70. And so what we do here is this extrapolation. We have these 2 parameters or this many-body model. The no-Gaussian model is defined by omega and Nmax. These effectively introduce UV and infrared scale or cutoff. And so for a large enough UV scale, so that you include all the physics, the process up to there, we extrapolate in the infrared length. So that's in a bit in analogy with the Lusher formula in where you extrapolate to infinite volume in lattice QCD for those who are into that. And I refer to these 2 papers for more on the relation between these 2 parameters and the actual cutoffs, and then this leading order extrapolation. As we will see, we have something very similar for the similar exponential behavior for the decay rate. So the point of this is that we extrapolate for large enough UV that is larger than, equal or larger than 1 GeV. These are green, red, and purple points here. And we see that the extrapolation is very well converged and spans a very small range of energies, right? And the accuracy then is similar for Nmax equals 70, but with this extrapolation. Okay, so it happens that the video it's on top of some of the phrases, and I have to keep moving it. Yeah, so that was for the nuclear wave function, and then we have the pion wave. As a first approximation, you can consider a plane wave. This makes both the analytical formula and also the implementation in the code much simpler and also faster, but as we saw from the theoretical references, that seems to be an important contribution. So we should include this final state interaction. What happens is that this pion nucleus strong interaction influences the emitted pion. And how you model this, how we model this. So this is understood in terms of pion nucleus optical potentials from pionic atoms. So pionic atoms are atoms where one of the electron orbiting electrons is replaced by a pi minus. This is sustained by the Coulomb interaction, but the strong interaction affects the corresponding energy levels. So it shifts them, and with this shifting and widths, you can constrain this optical potential. But that's at near threshold. The momentum is near threshold. So the momentum I probably did not stress this enough, but you have this momentum, this energy scale for the final outgoing pion. It's 114.4 MeV. So you need to extrapolate the potential to this momentum, and for this you supplement this data with pion nucleon and pi nucleus scattering data, so that you have the potential at the momentum that you have in our system. And then the emitted pion is mostly S wave with a very small contribution P wave, and the interplay between these two powers in this case contributes with an attractive final state interaction. And the point of all this is that it increases the rate by 15%, as we will see. I will show you numbers later, but for now, believe me that it's a very important effect also within this microscopic calculation. Yeah, that brings me to the final input, which is the weak operator. There are three possible transitions. As Albert was commenting, what's the role of the sigma? Well, the sigma can also, once you consider admixtures, it can also decay through the sigma. People have neglected this contribution before, and one argument, which I think it's not a good argument, is that it's a very small probability to the wave function. So the squared amplitude, or the probability, is of the order of 0.4%. But this is not how it contributes to the decay rate. It contributes by interfering with the lambda amplitude. So it's not as a squared, but as a product with the lambda, right? And if you're really considering 10% effects on the total lifetime, then you should consider this, right? So starting with the simpler one, the lambda nucleon pion weak operator, in this case proton pi minus. You have here the non-relativistic version of that operator. The square root comes from the isospurious degree of freedom, isospin of the lambda, and then you have these two amplitudes, the spin independent one and the spin dependent one. This operator selects for the isospin 0 in the cluster. So remember, it's isospin 1/2. So if this is isospin 0, this should be isospin 0. And then you have two couplings. You need data to at least two values to fix those two couplings. So one is the lifetime, which is precisely now, 263 picoseconds. And the other is the asymmetry in the direction of emitted particles in polarized hypernucleus. And for those of you who have used these couplings, you can notice that it's not, this used to be. People used -7 point something. That's been updated to -9 because of so we have made a new fitting to these two values with the updated value of the asymmetry from this paper 2 years ago. So this is already a bit of an update already at the weak operator level without the sigma. And then we include the sigma, which has this contribution. Note that we don't have B terms here. We neglect those. So that contribution is indeed small. with respect to the lambda, but within this contribution, the B terms are also much smaller, also in the lambda, right? And these factors, the square root over 3 and 1 over 3, come from uncoupling the isospin basis, because we work in the isospin basis, into the particle basis for which we know the couplings. So we don't have A and B, but we have two possible decays here. So we have, again, two values, and we need also to fix them. The sigma minus is fixed by the corresponding lifetime. But note that for the sigma 0, we don't have that lifetime, because this decay is displaced or superseded by the corresponding electromagnetic decay. So for that, we use the chiral Lagrangian prediction, which just adds a factor 1 over a square root of 2. So this is how we fix the couplings. We enter these two weak operators in the matrix element, and we will see that the sigma inclusion works in opposite direction to the final state interactions. It interferes destructively with the lambda amplitude, and it decreases the rate about 10%. So it's a relevant effect, as I'd say naively expected from that probability. Maybe not 10, but at least 5%. I think we could expect. Yeah, so good. I'm ready to show you the results. I hope it was more or less clear, these three inputs. So this is in gigahertz. Probably it does not say much, just a value by itself to you. It's in the right ballpark, let's say. It's weak times 10 to the minus 10 seconds, few hundred picoseconds, and in terms of decay rate, it's about 1 gigahertz. This is only lambda and this approximated wave function. So as I said, only taking this amplitude, this is 96% of the probability of the hypertriton. If you take only this S wave part of the wave function, this is what motivates some people to use these simpler wave functions, right? And if you see to what it connects in the helium, so the helium is divided in mostly two amplitudes, but one of these amplitudes does not couple through the weak operator with this hypertriton amplitude. But this one it does, and if you compute this is about 1.141 gigahertz. And this is to be compared. I put this to be compared when you include all the possible transitions, so the full wave function, but only including the lambda. And you see an increase of about 8%. So it's not a bad approximation, but we'd say it's also not good enough, and this motivates for the full microscopic calculation too. By the way, this is within the plane wave approximation to start simple. And then if you include the whole wave function and also the sigma part in the weak operator, you see that this works in opposite direction. It decreases about 9%. As I was saying, this is just 4% of the probability, but it's relevant in the decay rate. And then if you include the distortion of the pion, these decay rates increase by about 15%. So this table kind of summarizes a bit the most relevant effects and their size. Okay. Here I show you these two figures side by side, because I think we think they compare and correlate very well. So this is within this extrapolation with UV scale fixed. We see that it's converged after 1 GeV, but even though it's not fully converged a bit before that, we see that these two figures correlate very well. So the energy, and as we will see, the separation energy with the partial decay rate. And we can correlate this lambda scale with the corresponding separation energy of the corresponding wave function, and then the partial decay rate. And from that, we can infer with the protocol I showed in the beginning of this talk, the corresponding lifetime. And so we see that there is this strong correlation following the protocol between the lifetime and the separation energy. And we see that they are actually compatible with different heavy ion collision collaboration experimental data, but each with its own separation energy. And more than that, we can extrapolate the separation energy to the one reported by the star collaboration. And we see that if we do this linear extrapolation, as expected from the theoretical side, we see that the corresponding lifetime falls also within the star reported value for the lifetime. I'd like to end the talk before summarizing. How am I doing in time? I think it's good.
Yeah, you're okay. You have still.
I have time, right? Because it's 50, but we started a bit late. So I just have 2 more slides or 3. We have some theoretical uncertainties here, and I want to talk a bit about them. As I say, there are these, or you can understand this in terms of 3 levels: from partial decay rate to lifetime, the Manybody level, and the nuclear force level, right? So first, we have this relation between the partial decay rate and lifetime. We have some uncertainty there, but we decided to focus on the partial decay rate. But even if you focus on the partial decay rate, you have this, you have to use the Manybody method, then the nuclear force. So we'd say that the Manybody method is more precise than the input Hamiltonians, and it's under control. And then we have the nuclear forces, right, which serve as input to this Manybody no-Correlation model, ab initio model. And so the nuclear force, these are EFT potentials. They have a certain cutoff. This is an essential part of the theory, how you separate these scales. And then in the next to leading order sim family, you also have the energy, the lab energy threshold after which you don't include the data anymore in your fit of the EFT potentials. This does not happen in the hypernucleon sector. I think the data there is much poorer, so you don't have this freedom. Anyways, this in the hypernucleon, this is a continuous from 550 MeV to 700. In the nuclear part, you have these 6 values for this threshold, and then these 7 cutoffs. This makes a total of 42 Hamiltonians, all fitting the corresponding data. And so we want to, this is a level which we can actually study and see how this freedom changes our partial decay rate. So depending on which Hamiltonian you pick up, this will give you a different wave function. And although all the wave functions are good in the sense that they fit the data, in terms of the decay rate, which is not included in the pool of data, this might change. So we can study this uncertainty, and that we did. So in this figure, I show on the left we have the partial decay rate, on the bottom the separation energy, and the blue points are so you can play with these numbers, right? In the blue points we have fixed the hypernucleon cutoff to 600 MeV, and then we computed all these possible 42 wave functions and corresponding decay rates, and we see this strong correlation that I was showing previously still holds when we tune all these values. Then you can also go to the more extreme cases by playing also with tuning these hypernucleon cutoffs so that you get extreme separation energies. We see that the correlation still holds, although not probably as expected, not as clear. And we are not claiming that this wide range of decay rates is really the uncertainty, but it serves a bit as a diagnostic to show you that this freedom these Hamiltonians, although they fit the data, it can influence a lot on the decay rate. And this is because the separation energy influences a lot the decay rate, and at the same time is not precisely known, so it cannot be fixed with these Hamiltonians. Yeah, so that's it. That's the most of my talk.
Can I just put a question here? What is the uncertainty associated with the pion optical potential? Because for the pion, I see two strategies. One, you have a pion optical potential derived from medium to heavy atomic levels of pionic atoms. And the other is that you have a very well-constrained chiral pion-nucleon interaction that you could use in a kind of microscopical way to distort, to take into account the distortions of the pions. Have you thought about that?
Frankly, not.
Okay, so this.
But it's good to know. We are yeah. This uncertainty was not in the previous paper, and we are still working on that. Yeah, we are drafting some papers, so we might. It's a good question to have in mind.
Mm-hmm.
I don't think we are tackling the problem of the chiral part. We will use these optical potentials, which Jelly-Friedman has been worked on.
Oh, okay, great, thank you.
Yeah, I don't know if Daniel Gazda is here. Of course, feel free to to contribute if you know more. But yeah, so to summarize, we have carried out this new microscopic calculation about this partial decay rate that was needed because the last one was 20 years ago with these 9 megan potentials. And the main effects are that the pion final state interaction is relevant. It increases the rate about 15%. The sigma contribution, this was not done previously. It works in opposite direction. It decreases about 10%. And then there is a strong, probably as expected, but we put forward this strong correlation or dependence on the separation energy. If we deduce from that the lifetime, we see that each result is compatible or correlates well with the different experiments, the different heavy ion collision collaborations, but each importantly with a different separation energy. And then, yeah, that's pretty much it. I'd like to end up thanking my collaborators. I did not stress this in the beginning or during the talk, except maybe thanks to Angel's question. But this has been a truly collaborative work. My collaborators are Daniel Gazda, Abraham Gal, and Eli Friedman. Daniel Gazda, I'm sure you know him. He has been working a lot on hypernuclei and a punitional partial model. He provided the wave functions, insisted in doing all this testing in cutoff dependence and using all this family of 42 Hamiltonians. Eli Friedman, he's been providing these distorted wave functions and also testing different things. Abraham Gal he's Abraham Gal, you know him. He's pretty much led most of this project from the beginning and provided a lot of testing, a lot of checking, and a lot of knowledge in general. So I'm very grateful for them. I kind of focused on the weak part, put everything together, implemented all the wave functions in different formats. And yeah, I don't know if Asom is here, but she also thanks to her because she was the one who in the first place, I probably should have said this in the beginning, she was the one who in the first place introduced me to this system, to the hypertriton in my thesis with the non-mesonic weak interaction. So a very different thing. And long time ago, as I said, this has been a long-term project that has mutated into different things, but also thanks to her. And thank you all for your attention and your questions. Thank you very much.
Thank you, Axel. Very nice talk, and quite an impressive set of results there with lots of interactions. It's nice to see things being explored systematically as they should. I wonder if anybody has any questions. I have one of my own. I mean, you started the seminar by saying, and your results sort of indicate, yeah, this, and the hypertriton is almost like a halo nucleus, no? You have the deuteron, and then you have this lambda particle very far away. I wonder if this sort of linear correlation can be understood in terms of some sort of halo effective field theory or something like this, where you have this separation of scales of very far away, very loosely bound particle around the bound system.
So I don't know about what they do in the halo systems. For an IZFT approach, that was precisely done by the Hildenbrand and Hammer last year, where the small scale was the separation energy, and they found that it seems pretty much independent of that separation energy, the total lifetime. And then in the theory side, so this linear extrapolation that we used, that that was done already in the 60s, I believe, by Dalitz or one of these people. I think they use this closure approximation, and they infer this linear relation. So just some first order term. So that it's linear. The first order should be linear, right? Because for zero energy, it should be equal both lifetimes. For zero separation energy, so completely free. So also I refer to that. Yeah, I'm sorry, in terms of halo, I don't know, but it's probably a good idea, a different approach than the EFT work. I say.
Thank you, Axel. Any other questions?
Yeah, maybe I can ask. You used this isospin 1/2 rule in order to extrapolate the results today. So I'm wondering, I don't know much about this, so I'm wondering how reliable is this, or is this based on experimental evidence that this works nicely, or is there a theoretical support as well, or how well do you expect this?
There are some theory works that have supported, but I'd say it's mainly phenomenological. So it's an isospin rule. In principle, with interactions, there is no isospin, but if you say that if you add this isospurious 1/2, I'm sure people can say more about this, Angels or whoever. But if you put this isospin 1/2 into the lambda and then work out the isospin relations, not only I mean, this is well sustained by not only lambda nucleon pion vertices, but other hyperons also, and kaons and other mesons, well, at least kaons. So you see that it works out, this isospin rule, where you input isospin 1/2, you work out as if isospin was conserved, and you see that this satisfies the corresponding partial decay rates or the different relations between these mesonic decay rates. So I'd say that step is pretty solid, pretty safe.
I see. And regarding the total uncertainty, so is there really important to have a better nucleon hypernucleon potential in order to reduce it in view of the results?
Yeah, I'd say the data there, it will help. That's part of the uncertainty. But yeah, of course, hyperons, you need to produce them and then they decay. So it's not like the nuclear part, right? But yeah, I'd say next to leading order, hyperon nucleon EFT potential should be pretty nice.
Well, but even a better leading order, I think, would be useful.
Yeah, probably there is also some uncertainty in fixed the low energy constants fixed there.
Okay, thanks.
Yeah, actually, Axel, regarding this delta I, well, this delta I equals 1/2 rule, there is some uncertainty in this rule. Maybe I don't remember whether it's a 5% or 10%. I don't know whether you can play with that and see if this uncertainty is within the uncertainty already that you have from the hyperon-nucleon interaction, for instance.
It's in the same, yeah. Since
but you can have a look and see. And the same with the pion. I'm not an expert on the pion optical potential, but I don't know whether the uncertainty on the pion optical potential, this could be even larger than the uncertainty that you are examining on the different hyperonuclear interactions, for instance.
The final state interaction.
Yeah, I don't know. I'm not an expert, but
no, it's all good that you say these things. About the isospin 1/2 rule, as I recall, at the lambda sector, looking at the data, as I recall, it was not a big source, but it's true that it's a phenomenological rule, and maybe it is 5%. So we could check that too. Yeah.
Good. Are there any other questions or comments for Axel? If not, then thank you very much, Axel, and virtual clap from here.
Thank you for inviting me. It was nice to talk about this because it was a long-term project, and I was happy to explain it to you. Also, I kind of started the hypernuclear thing in UB, so in University of Barcelona. So I'm glad to explain.
And you are back in Barcelona now, so hopefully we'll meet again.
Yeah, I hope.
Person soon.
When are you coming to Barcelona?
I'll